Welcome back to the day 2 of our workshop on multiphase flows and applications of heat transfer. Today we begin our day 2 with Dr. Vishwanath Ganesan, who is joining us online. Dr. Vishwanath Ganesan holds an MA in mechanical engineering from Purdue University. His research focuses on thermal hydraulics test facilities, multiphase CFD code development, and cryogenic two-phase flow boiling physics. Currently a postdoctoral research associate at the University of Illinois at Urbana-Champaign. He works on transient two-phase flow for cryogenic propellant tank transfer and thermal co-design for future server systems. Dr. Ganesan also held joint appointments with NASA GRC and as a Ward A. Lambert graduate too. Today, Dr. Ganesan will discuss experimental, theoretical, and computational investigation of two-phase flow boiling heat transfer enhancement on structural cells. Welcome, sir.
Thank you for the introduction. So, good morning, everyone. My name is Vishwanath Ganesan, and I'm a postdoctoral research associate of Professor Nenad Milkovich at UIUC. The lady already gave the introduction of my prior work, but before coming here, I was at Purdue, where I finished my master's and PhD. And before that, I was a junior research fellow working for Professor Kannan Iyer at IIT Bombay. And prior to that, I do have a relationship with IIT Madras because I spent 4 years in Pampa Hostel as an undergrad. Although I was not IIT Madras undergrad, I finished my undergrad in IIIT DM Kanchipuram, and it was incubated in IIT Madras. So I do have very fond memories of IITM. So today I will be briefly going through the two-phase flow research conducted in our research group, which is the Energy Transport Research Lab, particularly on the experimental, theoretical, and computational investigation of two-phase flow boiling heat transfer enhancement on structured surfaces. So the boiling advantage is a well-known phenomena whereby utilizing the latent heat of vaporization of the working fluid, one can dissipate large amount of heat from a heated surface without incurring a significant incursion in wall temperature, as long as there is a continuous supply of fresh liquid to replenish the bubbles departing from the surface. So cognizant of the operational limits of the working fluid, as seen in this particular figure, appropriate working fluids are chosen for specific applications based on their working conditions. For example, although water is used for indirect single-phase cooling of data centers using microcoolers, a dielectric fluid with lower saturation temperature is used for two-phase immersion cooling. Similarly, water, owing to its high saturation temperature and high latent heat of vaporization, it is a much more useful working fluid when it comes to boiling water reactors. Whereas cryogens such as liquid helium, liquid hydrogen, liquid methane, and liquid oxygen are well suited to be used for cryogenic applications in space, in particularly the line chill down of transfer lines for fuel depots. So despite having a good understanding of working fluid selection for various high heat flux and ultra high heat flux applications, why do we still keep pushing the two-phase flow boiling research forward? It is primarily to exploit its boiling advantage for two-phase flow, for flow boiling, and to utilize it for the fullest, all the way from ONB, which is the onset of nucleate boiling, till CHF, which is the critical heat flux. So current refrigerant two-phase systems operate at a maximum quality of 0.3 to 0.5. Hence, is there a way where I will be able to maximize the exit quality and reach something as close as 1 with greater interfacial instability, thereby delaying the CHF? Because if I can do this, then I can truly leverage the boiling advantage. Because I do have nucleate boiling, which gives me the highest heat transfer coefficient. And as I go from nucleate boiling all the way to annular flow, I have the convective boiling dominance, which is good in the annular flow region. But there always comes a operational limit I'm unable to exploit the quality all the way till 1. I either go till zero point 0.7 or zero point 0.5 or zero point 0.8. So is there a way to completely exploit or leverage the boiling advantage to our use? So this is possible by using structured surfaces, and we'll explain these in the next slide. So to better understand the heat transfer enhancement on a structure surface, let us first consider the flow boiling inside a plain tube, but with subcooled inlet conditions. I want to use subcooled inlet conditions so that you can see the additional two boiling regimes, which is the partially developed nucleate boiling and the fully developed nucleate boiling region, in addition to the saturated flow boiling region. So if you see, there are multiple responses that we have when we have two-phase flows. Usually you can divide it into three. You have the hydrodynamic response, which is basically how the pressure is varying. I haven't shown it here, but you know how the local pressure is varying. Second, you have the vapor content response, and I show here that how is the vapor content varying along the axial direction. And the third is the thermal response. So thermal response can either be shown just as the temperatures, the wall temperature and the fluid temperature, or as heat transfer coefficients, which is the nucleate boiling heat transfer coefficient and the convective boiling heat transfer coefficient. So if you look closely here, the boiling incipience occurs only here. The boiling incipience occurs only when the wall temperature exceeds the wall temperature required for boiling incipience. And that is called as T-wall ONP. And as you move forward and you go into the saturated boiling region, in the saturated boiling region with more vapor generation that you have or more vapor content, what you observe is that the nucleate boiling gradually suppresses. And simultaneously, you have an enhancement in convective boiling, which you can see here. So both of these simultaneously occur. However, the boiling terminates, or the nucleate boiling terminates when the wall temperature goes below the wall temperature required for onset of nucleate boiling. And then beyond this, what you observe is something called a pure annular flow, which means when you're having annular flow, you don't have annular flow with boiling. You have an annular flow devoid of any boiling. You just have a thin liquid film near the wall that is eventually getting thinner and thinner by virtue of evaporation across the interface. But now, why is this process unstable? Because as the liquid film becomes thinner and thinner, there is a point where the strong velocity difference across the interface makes the film unstable, thus exposing it to vapor and causing partial dry out to occur. So this word is very important because you may not never reach to total dry out, which is when the quality is equal to 1. You will almost always reach something called partial dry out, which is basically when your quality has not yet reached 1, but because the interface has become unstable, your wall temperature started to excur and has started to go like higher and higher, and you are forced to shut down your system. So surface structuring, what is the advantage of surface structuring in leveraging the boiling process? So surface structuring aids first in premature nucleation, which means that I don't have to wait all the way till this T-wall ONB for boiling incipients, which means I can have boiling occurring at even lower wall superheat. And when we know what is the definition of wall superheat, it is T-wall minus T-sat. So if it is the lower wall superheat, which means your T-wall ONB is also lower. So you're able to incur premature nucleation. And not just that, by virtue of having low T-wall ONB, I can also prolong my nucleation over a long distance. Because like I said, when does the nucleation terminate? When the wall temperature goes below T-wall ONB. If the T-wall ONB is anyway lower, my wall temperature is free to decrease more and more and more by virtue of enhanced convection in the annular flow region. And I can still have a long region of nucleate boiling. Hence, I can utilize the latent heat of vaporization of the liquid, and hence I can get higher heat transfer coefficient. But in addition to this advantage that I get in terms of nucleation, in the annular flow region, when you have a structure surfaces, of course, we know that the annular film or the liquid film gets thinner and thinner. But in the annular flow region or in an annular flow region on a structure surfaces, as long as there is de-wetting of the surface, which means the interface has cut off and there is a presence of a contact line, then what happens? That contact line continuously rewets due to capillary effect. And it continuously rewets, and keeps pushing the stability of the liquid interface from getting unstable. Hence, pushing for higher exit quality. And or in other words, you are reaching close to one. It's very difficult to reach exact one, but at least you can reach close to one. So this is the overall like summary of why we want structure surfaces is mainly because I can utilize the nucleate Balling physics, which we'll go into the details later, unique to structure surfaces, but also use the capillary effect that is again unique to structure surfaces and push the exit quality to higher values. So having understood that structure surfaces help us, which surface is the best? We can definitely create. So in our lab, we have played with a range of surfaces for the different materials and different edge chemistries. But how do we come to a conclusion that which surface is the best? So for that, we can use the Seuss model or Seuss-Graham model, however it is taught in colleges, to understand which surface is the best. So the Seuss model determines the range of nucleation sites or the range of sizes of the nucleation sites that are activated based on two terms. The first term is the available liquid superheat, which is defined in this particular equation. So the available liquid superheat is primarily a linearly increasing function that you have, or it's basically linearly decreasing as you go away from the wall because you are in the laminar sublayer. And the second term that you need is the required vapor superheat. But this particular required vapor superheat is the superheat required to activate the said cavity. So what happens is that with increasing maximum surface feature size, the required vapor superheat also decreases because as you can see, the required vapor superheat relation actually comes from the Clausius-Clapeyron relation. If you rearrange that, and what you get is that for smaller cavities, you require a very high vapor superheat to nucleate, whereas a larger cavity requires a smaller vapor superheat to nucleate. So hence, as the feature size increases, the required vapor superheat also decreases. And hence, if the required vapor superheat decreases, it moves on the right side of the curve, because if you see the axis for higher temperature is going to the left. So now what happens, you actually get an intersection and you get a range of cavities. So what we can summarize this is that with increasing surface feature size due to etching, the required vapor superheat decreases and becomes sufficiently lower than the available liquid superheat for sustaining bubble nucleation at higher bubble growth rates. So hence, with the target to leveraging both the material selection and structuring techniques for heat transfer enhancement, we at ETRL have performed several pool and flow balling experiments that would be briefly explained in the subsequent slides. So this particular slide talks about the saturated refrigerant pool balling test facility, where the pool balling is happening on the external surfaces of the tubes, which are engineered surfaces. So here, without going into too many details, so as the working fluids are R134A, one R1336, MZZE, and MZZZ. And we actually use a range of combinations of material and etching chemistries to eventually quantify the performance of nucleate pool balling heat transfer. So this is basically a pool balling test facility. And this paper is currently under review, and we have even developed a new correlation for edge surfaces with an ME of 7.03 percentage. But in this particular setup, what we can understand is that there are different levels of responses. One is the macroscopic thermal response. Like I had earlier told, there is a hydrodynamic response, there's a thermal response, and there's also vapor content response. So here what we observe is that in this particular setup, we can only get the T wall and the T sat along with the pressure as the system level macroscopic hydrodynamic and thermal response. Next, we move to the water flow balling test facility, where we perform the saturated water flow balling tests on both aluminum and copper microstructured surfaces. So here we use the externally heated tape heaters on brass blocks to heat these copper or aluminum tubes, which you can see inside. We have a flow visualization test section, which we later use to make or improve a flow regime map. This is the improved version of the Thomis flow regime map. And for this experiment as well, we have, where is it? Yeah, we have these particular macroscopic and microscopic thermal responses. So till now, you don't see any microscopic thermal response or hydrodynamic response that we can get. But what you see is that we can get the macroscopic thermal response from the thermal point of view and the hydrodynamic response. But in the macroscopic thermal response, I just want to point out that we find the thermodynamic equilibrium quality, which is not necessarily same as the flow quality. And we will discuss this more in detail in the subsequent slides. Next, we also have a saturated refrigerant flow balling test facility, where we test for both a single component and multi-component, or in other words, refrigerant blends. And in addition, instead of using any rope heater or tape heater, we here actually use a secondary water loop to heat the refrigerant in the test section. So on the right side, you see certain snippets of the thermal response that we get for all these different working fluids under these operating conditions for different vapor qualities or local vapor qualities, all the way up to dry out type CHF. And in the bottom, you see that we also have found out that of all the frictional pressure gradient correlations, the Friedel, which was developed in 1979, along with the Lockhart-Martinelli correlation for estimating the void fraction, actually gives us the closest prediction of the hydrodynamic response, which is the pressure drop in this case. So again, to give a good, I think there are students as well here. So when we have two-phase pressure drop, it is usually divided into three components: the frictional pressure drop, the accelerational pressure drop, and the gravitational pressure drop. Gravitational pressure drop is purely, you have to use the correct void fraction relation. For frictional, you have to use the correct model, because you have either the homogeneous equilibrium model or the separated flow model. So Friedel that you see here is basically a separated flow model based relation. And then you have the accelerational pressure drop, which is primarily by virtue of phase change. And again, there you need to use the correct formulation for void fraction. So that's why here I said the Friedel is the correct form that we use for the separated flow model for the frictional pressure gradient. And the Lockhart-Martinelli void fraction relation gives us the best prediction in this particular case. And in this particular case as well, we are only limited by the macroscopic thermal response, which is the same as what we saw in the previous slide. So both the prior and most of the experimental test facilities that we see, I'm just checking the time, I have 30 more minutes. So both the prior and most of the experimental test facilities only use or only provide us with the macroscopic system level responses that are made available to us using physical sensors. As you can see from this particular slide, for every control variable for which you have the operational variable and the geometric variable, you get the hydrodynamic response that you saw for most of the slides as the pressure drop. Again, not local pressure, because for that you need to have multiple pressure tabs. Sometimes people only have two pressure tabs, one at the inlet, one at the outlet. And then you get the thermal response, but only macroscopic in terms of ball temperature and the bulk temperature or the bulk fluid temperature. But the bulk fluid temperature is again basically just simple energy balance. So again, you are not finding that experimentally. And then when it comes to vapor content response, again, you don't find anything experimentally, because I'm pretty sure most of us don't find the actual flow quality or the actual void fraction, but rather we find something called the thermodynamic equilibrium quality, which is quality at any location is equal to inlet quality plus 4 into the boiling number into Z by D. And then in addition to that, we get the transition point response, both at the onset of nuclear boiling and at critical heat flows. But despite this, there are still a lot of macroscopic system level response variables that are still unavailable. So we won't go into this detail because that's not part of this presentation. But efforts has to be made to even identify these variables as well, because they all talk to each other, and having all this information is necessary. Now, is this enough with our goal? Like these macroscopic variables that we have, is this enough with our goal to exploit the Berling advantage using structured surfaces? Or is there an additional need for microscopic surface level responses? So for that, we can take a step back and look at the evolution of predictive tools for flow Berling heat transfer coefficient and dry out determination. From mechanistic models with great physical insights but overly simplified to data-driven models and all the way to computational models that rely heavily on the accuracy of near-wall heat transfer and mass transfer physical models, we have gradually been pushing towards unveiling the physics fundamental to flow Berling. It's not just our group, but even at IIT Madras along across the world. Hence, there is definitely a need for high fidelity experiments to develop fundamental understanding of local flow Berling physics. And for this, we need to identify a reliable method to analyze the near wall microscale physics. So this slide shows the limited microscopic surface level response that we at UIUC were able to achieve using an in situ boroscopy to better understand the bubble nucleation and departure dynamics of isolated bubbles during saturated flow Berling of refrigerant R515B. The unavailable high fidelity responses are highlighted in the red, and I'll go through them one by one. But for those interested, please look at this paper. This was recently published in Science Advances. To the best of my knowledge, it is, I think, the first and the only flow Berling paper to ever be published in Science Advances. It's a detailed paper with a lot of supplementary information as well. I participated as the second author of this paper. So please do take time later and read into these particular discussions. So the advantage of boroscopy, in addition to getting the trivial information that we need, which is basically the nucleation site density, the bubble departure frequency, the bubble growth rate, and the bubble departure diameter. So these are the primary response variables that you can get from the boroscopy, as you can see from the figure on the right. But using this and processing this information, you can even perform something that we did, which is the bubble departure analysis, where we prove that the unsteady growth rate is the dominant force that is actually acting in the downward direction that holds the bubble. And that is the primary force that determines the bubble departure diameter. Uh, in addition to that, we do quantify the effect of mass flux, heat flux on both the shear lift force and the buoyancy force, which is pretty much as expected. As you increase the mass flux, your shear lift force increases, and as you increase your G, your buoyancy force decreases, and as you increase your heat flux, your unsteady drag force increases. So this is the negative direction because it's acting in the minus y-axis. It is increasing, and that is mainly because with higher heat flux, you have higher wall superheat, and higher wall superheat leads to higher unsteady drag force. So the microscopic, the surface level high fidelity data links the near wall physics to the enhanced Berling heat transfer response. Now, so hence with this newly found method, we have modified our refrigerant flow Berling test facility, and we have been using that to, as you can see here, to analyze a lot of different physics. So one is we do have boroscopy near the inlet to see the fluid physics of isolated bubbles or the bubble dynamics of isolated bubbles. And then as you go to midstream, we actually do the flow regime transition analysis in the midstream, where we see that when is the flow transitioning from bubbly flow to slug flow all the way to pure annular flow. When I say pure annular flow, remember what I said. When the wall temperature goes below T wall ONB, which means the boiling has completely terminated. And what you should see, as you see here, is pure film. You shouldn't see any bubbles. You should see a pure liquid film. And using, again, the boroscopy at the downstream location, we also try to unveil the physics unique to structure surfaces on the dry out mechanism. In other words, how is the capillary effects helping in pushing the exit quality, or it is helping in restabilizing the interface that is continuously getting destabilized because of the strong velocity difference across the interface. But now, as you see, in addition to the macroscopic responses, well, now we also have some microscopic thermal response, but again, it's limited. You do need additional microscopic thermal responses, but again, there is a huge curve, a learning curve from experimentation point of view to get those particular data, which we are currently pursuing at ETRM. So now going into the details, not to go to spend too much time on this, but you feel free to learn from this particular slide that what kind of boroscope we used. So we used two kinds of boroscope. One is the Hawkeye Pro Micro Slim, primarily because of its lower diameter and lower field of view, which was used in the upstream region to understand the isolated bubble dynamics. And we used the second boroscope, which was the Hawkeye Pro Hardy, which had a broader field of view, which was primarily used at the downstream to characterize the flow quality, the flow regime transition, and the dryout. And like I said, in this particular presentation, I'll be focusing only on R515B as a refrigerant, which is a low GWP fluid. Okay. So before we go into the physics and understanding all the physics unique to structure surfaces, let us just look at the preliminary data that we can get from the boroscope kept at the upstream condition to understand the isolated bubble dynamics. So from the heat transfer enhancement point of view, we observe that the etched aluminum surface boosts the heat transfer by 211% by creating smaller and more frequent bubbles and reducing the wall superheat. Remember, like I said, more bigger the size or bigger the surface feature size, lower is the vapor superheat required for a bubble nucleation. So hence it is nucleating at lower wall superheats. Next is the bubble dynamics. Edge surfaces have more nucleation sites. It's of course is obvious, and they have smaller bubbles because they are departing at smaller bubble sizes with lower departure frequency and slower growth rate due to the reduced wall superheat and higher wettability. From the force balance point of view, the lower surface tension and the unsteady drag forces on the edge surfaces result in smaller bubble departure diameters. So that's what I told. On edge surfaces, you have lot of small bubbles departing at lower wall superheats, as opposed to, let us say, water on a plane surface where you might have smaller number of larger bubbles departing at higher wall superheats. And now let's understand the wall superheat impact. So lower wall superheat on edge surfaces slows down the bubble growth rate and hence also reduces the departure frequency, whereas the higher heat flux increases the drag force. And for mass flux effects, increasing mass flux slightly reduces the bubble departure diameter, but the unsteady forces remain dominant, or the unsteady drag force remains dominant because they are primarily a function of heat flux and corresponding wall superheat. Similar observations were also observed on etched copper. But you can see something weird here. You can see that I'm not observing like the same enhancement in nucleation site density or even the heat transfer coefficient. The plane and the edge kind of look like overlapping on each other. So why is this? And this is something we'll be discussing in the subsequent in the subsequent slide. So we have two of similar structures with widely different heat transfer coefficient enhancement levels. So we do understand edge surfaces or structured surfaces, or in this case, when you're talking about edge surfaces, they're primarily hugely dependent on the edge chemistry that you are using to create these surfaces. So it is all basically a surface driven physics. Material wise, yes, they are two distinct materials, but the physics that is aiding in both nucleate balling as well as surface rewetting or the rewetting in the annular flow region I'm talking about is primarily determined by the surface driven effects. So how to prove these surface driven effects? Like how shall I prove that aluminum or edged aluminum was more conducive to create better nucleation sites and create better heat transfer and do better surface rewetting as opposed to etched copper. So how do we? So for this, we know there are several traditional surface characterization techniques, from SCM to confocal microscopy to atomic force microscopy. But what do we need here? So we need the quantitative data on pore size, because remember, I'm talking about cavities. So we need quantitative data on pore size as to be able to confirm whether the structures on these surfaces are in the optimal size range offered by the SUS model. Remember what I said, SUS model gives you the range of the sizes that can be active for a given wall superheat, or for a given condition. So what is the range of sizes? So for that, what we prefer to use is the method of mercury porosimetry, because that provides us with the quantitative measurement of pore size distribution, the quantification of total porosity, and the volume of pore volume, and the determination of pore volume and surface area. So it's about the pores for the cavities. So here on this particular slide, on the top left, on the top right is where you see are the results from the SUS model, where for every given wall superheat, like I said, you get a range of cavity sizes that the model determines that they need. Like this is the range between. This is the range of sizes that can be activated. These sizes, this pore sizes or cavity sizes can be activated. So for a given operating condition and for a given R min and R max, we actually compare with the cumulative volumetric results that we get from the porosimetry, and we actually find that for the range that we are talking about, the range of cavity sizes, we actually see there are always pores that exist in the etched aluminum surface in these sizes. That's why its cumulative volume is increasing. Whereas on the etched copper surface, we actually find there are some regions where there are no pores at all. And you can see the volume, how much it is occupying, as opposed to the volume that you see on the etched aluminum surface. So which means that just making an edge surface is not enough. The chemistry of creating those edge surface should be so good that you can create those pores or those cavities that you can exploit for both nucleation and later on for interfacial stability, for pushing the exit quality. I have 12 minutes. Yeah. So here is where I want to take a step, because although this is not part of this particular lecture, but I want everyone to understand, especially there are students here, what is the big difference between the thermodynamic equilibrium quality and the actual non-equilibrium quality. Okay, so actual quality, in other words, if you call it flow quality, it's basically the ratio of m dot g by m dot, the vapor mass flow rate divided by total mass flow rate. But the actual, but in reality, when people use the word quality, they use it very loosely, and they use the thermodynamic equilibrium quality, which is XE, and they define it as that is the quality, but it's definitely not true. And the relation that equalizes it is basically the energy balance. So the enthalpy that you get from energy balance can be same as the enthalpy defined using equilibrium quality, and that can also be same as the enthalpy defined using the actual quality. So the equilibrium quality is pretty much straightforward. Everyone should know this: HF plus X HFG, or 1 minus XC into HF plus XC into HG. And then when you come to the non-equilibrium part, you introduce the non-equilibrium effect. Now, what is the non-equilibrium effect? It is the liquid superheating effect. It is the vapor superheating effect, which means the vapor temperature and liquid temperature are not in thermal equilibrium. Or in other words, in saturated flow boiling, you can say your bulk temperature from energy balance may be at Tsat, but your vapor superheat or the vapor temperature might not be at Tsat. It might have higher superheating to that. So when you rearrange and under certain assumption where you assume that the fluid is in Tsat in saturated flow boiling, but you don't assume the vapor is at Tsat, you still allow the vapor superheat to exist. then what you get is the relationship between the actual quality and the equilibrium quality. So this is from my 2022 paper from my cryogenic study, where we developed the actual quality correlation for liquid nitrogen. But nevertheless, the point here is this: only under zero vapor superheating effects does your XA becomes same as XE, which means your thermodynamic equilibrium quality is your theoretical limit, is your maximum theoretical limit, which says that all your vapor is, or all your liquid is converted to vapor with no superheating effect. But if there is any superheating effect, then your XA or the actual quality will always be less than equilibrium quality. As you can see here, your actual quality from experiments by Professor Rosenau at MIT, we see that the actual quality is always less than X. So why did I bring this topic? Is because we actually proved this hypothesis at UIUC. So in this slide, we show that we indeed get higher actual quality on the edge surface, where the actual quality or XA is reaching its theoretical maximum, that is XE. And this is possible due to the bubbles nucleating and departing at lower wall superheats. If the bubble is departing at lower wall superheats, why should it be attached to the wall? It is so happy. It's growing and departing at lower vapor superheat or lower wall superheat. So more bubbles are getting departed, and hence you are reaching the theoretical maxima of quality, where there is very little vapor superheating. And so this is where we are able to see, and this is possible due to the bubbles nucleating and departing at lower wall superheats, ergo lower vapor superheats due to the increase in the cavity sizes, which reduce the vapor superheat required for boiling. Okay. Now, next, as we go to the subsequent boroscopy regions, we also observe the boiling suppression region and the flow regime transition region. Oh, the video is not playing. 1 minute. Or is it playing? Okay. So yeah, so the thing is, like I said, we observe, like I said, the transition to the pure annular flow occurs when the wall temperature reaches below T wall ONB. So we do observe. I think the video is not playing. Now it's playing. Okay. So we do observe that on an edge surface, we are able to delay the transition to pure annular flow all the way till the end. Because like I said, the T wall ONB itself is less. So as the wall temperature is decreasing, it's happy. It's like, thank you. It is your wall temperature is still higher than T wall ONB. I would still nucleate, and I'll help you with nucleate boiling heat transfer coefficient. And I'll go all the way till the end, till when the wall temperature goes below T wall NB, and then I'm sorry, I can't help you with nucleate boiling. But hey, don't worry, I still have re-wetting effects, because I have good, like I said, we have a capillary effect that is going to occur when even there's interfacial instability, or there is like de-wetting of the surface, then the contact line would move closer and again keep re-wetting the surface. So hence I can push my quality towards 1. Of course, it won't ever reach 1, but you can push it towards 1, and at the same time leverage or exploit your nucleate boiling or the boiling advantage that the fluid is offering to you for this particular application. So now, coming to the last few slides, here is where I have 5 minutes remaining. So here is where I would quickly go that this is the project that we are working in collaboration with Raytheon in the United States. So it's a proprietary code of them, so we don't have access to that, but I can definitely give you an overview of what we are actually doing. So we are leveraging, like I said, both the experimental and the computational capabilities to come up with a computational model that not only relies on the macroscopic physics, but also on the microscopic physics. And how do we give that? We give them to them by using our confocal microscopy and then mercury porosimetry, all those metrology techniques to give them the surface feature physics. And in addition to the bubble dynamics physics, like the bubble departure diameter, the nucleation site density, bubble departure frequency, and all of this we give to them, and then they are able to simulate both the nucleate pool boiling physics and even the flow boiling physics. which is in this particular case is morely convective bowling driven because you don't see any nucleate bowling here. It's at high quality region and it's for nucleate bowling physics. So how this multi-scale computational framework works is we basically do a DNS come LES coupled simulation where near the wall we have like an adaptive mesh refinement technique where we use DNS simulations near the wall, and as you go away from the wall, it goes to the LES formulation, and overall it uses the volume of fluid equation because that is the single component two phase equation that is being solved in this particular case. And for certain details, there are like how the information of the surface is feed to the simulation is by using the statistical representation of surface roughness, where basically we give them two values. This is like a Gaussian distribution that they kind of get, and what they use is or what we give them is the standard deviation and the mean surface roughness information that we give them, and based on that, like I said, they have a near wall DNS simulation, and as they go far field or far away from the wall, they go to an LES formulation. But all in all, it uses the volume of fluid formulation to solve the heat and mass transfer across two-phase flows. So this is one of the model results that we have currently for adiabatic two-phase flow as well, because adiabatic two-phase flow is important because when you have flow visualization, it is definitely not being heated unless you have an ITO, coated heating. But in this particular case, I'm not discussing that, but we are working on that particular case. But here it's adiabatic on just a flow visualizing section. And so we compare that with the experimental data that we have. So you see the simulation on the left, experimental result on the right. And then we are also testing it for either other diabatic systems, which means you are having heat transfer given or the heat flux is being provided. And then we are comparing the experimental wall temperatures to the predicted wall temperatures or the predicted heat transfer coefficients in this case. So the comparisons are reasonable, but we are still in the process of publishing this work. So that process is going on. And with 3 minutes remaining, maybe for Q&A, I want to thank you, especially Professor Arvind and Professor Ninad, for giving me this opportunity to discuss our research. And I want to also acknowledge all our sponsors who have been critical for funding us. And this is our team. It's a very big team. I do encourage graduate students who are soon to pursue PhD or postdoc to please reach out to Professor Ninad if you are interested in doing one of these research. So thank you, everyone. This is my presentation.
So thank you, Vishwanath. So we have a few questions from the participants here.
Yes, Professor.
Professor Sanjeev.
So what properties of the structured surfaces are really important for the heat transfer? You talked mostly about the roughness or the pore size. What are the other critical properties for this?
You are absolutely right, Professor. We are working on understanding other properties that might be important. But since we are primarily talking about enhancing boiling, so the cavity sizes or the feature size or the pore size or the structure size primarily becomes the most important criteria for us, with the objective to enhance nucleate boiling and also introduce the capillary effects at the end of annular flow boiling where we can utilize that. But talking about different properties, I can definitely tell that the structured surface is definitely not so. It's a very loosely used word, so that's why I was very careful to use edged surfaces because there are any surface with, like you said, roughness or anything can be categorized as structured surfaces. Some people would even say like they won't call microfinned tubes as structured surfaces, but they do observe some heat transfer enhancement even on microfinned structures or microfinned tubes. But properties in terms of how good the heat can, first is how the heat can transfer through that media. So of course, thermal conductivity definitely plays an important role. In addition to that, the liquid surface combination also plays an important role. In other words, the contact angle. So of course, I can make sure that these are hydrophilic surfaces where the contact angle are very small. But that's a joke here, because if you remember the original SUSE model, there is a limitation on the contact angle, because the contact angle is limited by the cone angle of the cavity. So they say that the contact angle should not be so low. It should be a bit higher than the cone angle for the vapor embryo to be trapped. As the liquid front is coming, the vapor embryo should be trapped so that the vapor can grow. But then now what we are observing is that even for surfaces where the contact angle is close to zero, I'm still observing nuclear volume. So what you asked is a very deep question, and we are thinking of even some concepts like nanobubbles. That is basically moving away from the classical nucleation theory, that there might be presence of some dissolved gases or some nanoscaled bubbles that can be the one who are basically carrying the effect of enhanced nucleation, like the genesis, and then they take away and they take over the entire size of the structures. So yeah, in summary, I would say, since we are focusing on the boiling, focus has been on the pore sizes, but I do understand there are other properties that can be playing a vital role, and it has to be investigated further. But if you have any suggestions or inferences, please feel free to tell me. I would learn from you. Yeah.
Thank you.
Yeah, Professor Peter. Yes.
Yeah, thank you very much for this interesting talk. When we saw the etched aluminum and plain aluminum and etched copper and plain copper, we saw very nicely, I think, that one major thing to enhance heat transfer coefficient is the active nucleation site density.
Yeah.
It's the nucleation site density that is responsible for the heat transfer coefficient. However, when it comes to the modeling, and you showed these very comprehensive models, including contact line modeling, including nucleation models. Yeah. Specifically, the nucleation model. I mean, whose model gives you an indication where it should be, in which range it should be. But
I agree.
it's not really predictive. So
No, it's not.
What kind of predictive models do you use when it comes to the modeling? Because you presented also very nicely simulations, which seem to fit very nicely to your experiments. But it's extremely difficult to have a predictive active nucleation site model. So
I agree with that. So I think you might be aware of MURI, the multi-university research initiative. So we are part of a MURI project where we collaborate with Professor Yunjin Wan at University of California, Irvine, Professor Bucci at MIT. So what we are doing is using machine learning in a way. So we are, again, I should be careful, because machine learning is more of like a training. So you still need information to train the models correctly. But we are using this high fidelity techniques. What I presented was just our technique, which is the boroscopy technique. And like I showed you in the very, very early slide, because I didn't go into the details because that was not part of this particular presentation, but we are also using this slide. Where do we go?
yeah, but on this slide,
Yeah, we are also.
There's
Yeah.
nucleation submodel. So what kind of nucleation submodel do you use as a predictive model?
Oh, you're talking about the computational side?
Yeah.
Okay, the computational side. Okay, so I'm not so privy to the details because the Raytheon has those codes with them. But what I'm aware is that they are using for the. So I think Professor Dheer had some model for the micro layer thickness. It was some kind of a fourth order ODE or certain equations. But what they have done is that they've used a method of moving asymptotes.
Yeah.
So they have used an asymptotic
variation. That's the question. To get the active nucleation site density, it's before the bubble is there. It's the initiation of the bubble.
Right.
Active nucleation site density is the most important thing, as we saw. I think the initial nucleation
Yeah.
predict this. This is a major challenge. Yeah.
Right. So, Professor, if you remember in the slide, I told some information we give to the model. So we actually give based on our whatever low fidelity or whichever fidelity experiments that we have using boroscopy, we give them a representative nucleation site density or the number of nucleation sites per millimeter cube or per millimeter square in this particular surface. How much are the nucleation sites that are getting nucleate, or many sites are getting nucleated with the mean surface roughness and the standard deviation using the profile for the surface. So that information is provided.
Okay, so at the moment it comes from the experiment, not basically from the experiment. Not.
Let me, I have to go to that slide.
Maybe
1 minute.
Into the literature, into your papers. Yeah.
Yeah. Oh God, where is it? Here. So this information we give, which is the bubble, N here is the nucleation site density. So we give this information to the model, and then they are able, that's why this computational model is later going to be even used for a structured surfaces. Because I don't think there is any current predictive or a semi-empirical model that is tuned for structured surfaces. It might be for plane surfaces. But here is where we are doing the synergy of bringing in some information and then seeding it or giving it or feeding it to the model and see how it evolves and how it is able to like find the physics at steady state or basically at every time step till it reaches steady state.
Thank you.
So I have.
Yeah. You have to be a little louder because I think the microphone has to maybe come front. Maybe these microphones have to pick up here.
So, Professor, you're able to hear me?
I can hear you.
Yeah. So my question is specifically with respect to the modeling choices that you made. Like, interestingly, you mentioned that, for example, you are using DNS close to the boundaries in the flow boiling case and LES like inwards. So is this choice, is there any specific reason for this choice or?
Yeah, the reason is the feature sizes, because boiling is a multi-scale physics, and as you go closer and closer to the wall, you see different scales of bubbles, and the flow physics is much more complex for boiling. So since we know that the boiling is occurring near the wall, there is where we need a higher resolution. But then as we go into like far away from the wall, then it's primarily a macro scale physics where you still have evaporation, but not boiling. It's just evaporation. The bubbles are going and their phase changes occurring along the interface. But it's the boiling physics that is the most difficult to capture. And that's why DNS only near the wall.
So my question is, like, since you are using the VOF also, so you are resolving the interfaces also, is it like in the future, should we see a DNS at the core of the pipe also? I mean, do you feel LES is enough or do we have to move towards DNS?
I would say LES should be enough, mainly because we know that the volume of fluid is very good for free surface flows. That's why people, when they do film boiling simulations as well, they don't worry about anything because it's a free surface. We have a free interface and just macroscopic mass transfer happening across the interface. It's only when you come to the microscopic scales, and especially near the wall where you have boiling physics, is where the issue is. So that is one of the reasons why they did. Both, of course, from computational time, they want to save the computational resources, so they make use of adaptive mesh refinement. But in addition to that, I still feel we don't need probably, but again for this problem. But if you have like problem like atomization or something, where the multi-scale physics is not necessarily, there's no wall anymore. Like there's just atomizing. The jet is coming through a nozzle and it's atomizing. In that case, maybe you need DNS all the way through the entire flow field. But here, since it's boiling, we are only, in my humble opinion, I feel it should be only near the wall. But if things change, you would be the first to know because we'll be publishing and you can see if it changes.
Thank you, Professor.
Yeah.
Thank you for this very interesting presentation. I think that after 30 years in the field, there is something that is always constant in the boiling, is that we have plus minus 30% of accuracy in predictions. So, because mainly the reason is that boiling is a stochastic phenomenon. So you are not able to track down all the possible variables and features of the surfaces and so on. So at the end, we are always landing. We are very deep in trying to have very good measurements techniques and so on. But at the end, the prediction that we can do is always plus minus 30%. In the best case. In the best case. 35, 30%. And this is, for example, I just wrote a review paper about the fact that CNT, the classical nucleation theory, is not working for most of the cases. and the another point is that, in fact, what you said about the nanoscale phenomena is really important, but then it's becoming really unpredictable because we cannot see the bubbles at 3 nanometers, but they are really the beginning of the boil. So what's happening is at that scale. So it's not a question, it's a kind of comment that we are doing very, very accurate, experiments and so on. But at the end, we have this kind of output plus minus 30%, which is still there. So
I agree with this.
So Vishwanath,
Just to add, sorry, Professor. Just to add to Professor's thing, Professor, this might interest you, but we at UUC have been trying to use AFM technique because there you can go to nanoscale. So although it's very risky, but we are trying to see just before nucleation. Just before nucleation, like we are slowly heating. So we have a AFM setup where we can put water and heat it using not a traditional heater, but it is inbuilt with a heated base where it's a constant temperature feedback that it does. So we are trying to see on any substrate just before nucleation, can we see these nanobubbles? So we are trying to see like if some genesis can be observed there. Because you have been so kind in sharing your views, it's my responsibility to tell that even at UIUC, Professor Ninad and me and we all of our boiling team, we are thinking of working on that as well.
I can add to this that our, let's say, stochastic fluid mechanics, fluid dynamics simulations are proving that even if you have one single nano spot, so a very small difference in the domain, this is changing completely the situation. One single spot of 2 nanometers is enough to change the condition at, let's say, 1 micron or 2 microns. That is really what you observe then with the boroscope and so on, because your boroscope is something like maybe it's 5 micron per pixel, means that you can detect the bubble when it's 20 microns. So it's really, let's say, 1,000 or even more, 10,000 times bigger than what is happening at the nanoscales.
I agree. Thank you so much for your insights. It was really nice. Thank you.
Vishwanath, I have one question. You were talking about the instabilities in boiling, flow boiling. So the results that you primarily showed are for large size channels. So did you also use these edged surfaces on smaller channels like mini channels and micro channels? And did you do it?
Beautiful question, Professor. And we are doing that. So some of the things I can envision, of course, are like confinement effects, because with too much vapor production, it can most probably happen that the bubble the order of magnitude of the bubble size is the same as the order of magnitude of the channel size. And then you can get like confinement effects where there's liquid has no place to go and wet the surface and you get a premature CHF or like, and then even other instabilities that we know. So we are doing that. That is not part of this particular lecture, but we are planning to do that. It is part of, again, the MURI project where we are testing this on different length scales. And yeah, it's an ongoing project. I don't have the results right now because till now they were still at macro scale level, but smaller scales, definitely there will be a problem. And that's where the idea here is that how to tune these surfaces. So very beautiful what you said, because there's no single answer here again. When I say that use edge surface, this, again, like you said, there's a question now. What if I have a small size diameter? Can this same edge recipe give me what I want? It might give me high heat transfer coefficient initially, but then with this huge creation of bubbles, suddenly it coalesces, creates a confinement effect, and then suddenly it gives me premature CHF. So did I win or did I lose? So at the end of the day, it's like a holistic answer one should give, and that is one of the objectives of that MURI project that we are doing, where we are trying to do a series of experiments on different channel sizes, different structures, different fluids. So we are actually building something called a universal test rig, flow bowling test rig, with even different inclinations and everything, like different flow orientations, to actually get all these data to, like Professor said, error percentage is always 30%, but try to at least get some physical insights on what is the proposed, like a design criteria that we would like to give to the audience.
Thank you very much, Vishwanath. In fact, some of these open-ended problems are required for us to hold future workshops on this topic. Otherwise, there is nothing more to do in this. So
We'll come again.
we'll come again. Yes.
Yes.
So thank you again. Let us give a round of applause.
Thank you, Professor. I'll stop my screen. Yeah.
Sure, and we will also send a small memento as a token of our appreciation across to you. Yeah, thank you so much. Yeah.
Thank you so much, Professor, and thank you everyone for